Hello everyone and welcome to lecture today. Today we're going to be discussing what's called mathematical induction, and we'll talk about the basic form of mathematical induction as well as what's known as the strong form of mathematical induction. This is going to be a little bit different than the stuff we've been talking about, but it's going to be useful when we're talking about relations and actually proving certain things about relations. Which is why we're kind of making the jump into induction a little bit early. So the mathematical induction can be loosely defined as the following. Is a logical method of proof that is based on the modus ponens rule of inference. Specifically, it's based on the following idea, the following rule of inference. If we have a predicate P of n depends on n in the natural numbers, or the positive integers, any countable set, and we have that P of 0 is true, and for all k in n, P of k, if P of k, then P of k plus 1. So we have this following statement that P of 0 is true, the predicate at the initial value is true, and for all k and n, P of k implies P of k plus 1. Then we conclude that for all n in the natural numbers, P of n must hold. Or put a little bit more compactly, if P of 0 is true and for all k in n, P of k implies P of k plus 1, then we have to conclude that for all n in n, P of n. And this statement right here is a tautology. And the analogy, I'm going to think of this figure that I'm about to draw as a sort of analogy. Think of a sequence of dominoes as an infinite sequence of dominoes. And the idea here is that in an inductive proof, typically we will show the first few cases hold. So P of 0, P of 1, and P of 2, say. Typically you only need to show the first statement is true, but if we can first start off by proving that the first couple statements are true, and then we can show that for all integers, if P of k is true, then P of k plus 1 is true. It's like we're thinking of the dominoes falling over. So P of 0 implies P of 1, P of 1 implies P of 2, P of 2 implies P of 3, and so on and so forth. This procedure extends infinitely, and we get that the statement holds for all positive integers or for all natural numbers. So this is a very, very good analogy to think about, this domino analogy, and very kind of clearly shows exactly what we need to do in order to construct a proof by induction. We first consider what's called the base case, or the base cases, and we need to clearly show that the base cases hold. And once you've shown, you only really need to show one base case, but typically it's good to show 2 or 3 base cases, just to very clearly make a clear argument that the proposition is holding for these introductory cases, these first couple cases. But then once we show the base case, we have to do the inductive hypothesis, which is to assume that for some k, P of k is true, which is evidenced by the base cases that you've shown. And then the last thing that you need to do is what's called the inductive step, which is typically the trickiest part of a proof by induction, because you have to show the implication that if P of k is true, then P of k plus 1 must also be true. But once you show this, you successfully prove the inductive step, then you conclude by this logical argument that for any arbitrary n, the statement P of n must hold, because you can use the inductive step to get to any n that you want. So I'll write this out, start with the base case. Which is showing the proposition for the first couple possible base cases. I'm going to put 3. You don't the first 3 cases. You don't need to do the first 3 cases. You can just do the first 2 cases. But typically I like to do the first 3 cases just to be very, very sure of where I'm starting from. Then you do the inductive hypothesis step, which is to assume that there exists some k such that P of k is true, which was evidenced by doing the base case and showing the base case for the first couple bases, or the first couple starting dominoes, if you will. And then the last step is to do the inductive step, which is to show that for all k in the natural numbers, if p of k is true, then p of k plus 1 is true. And this is the format of any proof by induction. Now there is something called strong induction. Induction is in chapter 5.1 in our book. Strong induction is chapter 5.2. I'll talk about strong induction a little bit later on. But for the first couple examples, we're just going to focus on the standard induction. And so what I want to do is really cover a number of different examples to make you feel at home with this method of proving things. So what we'll start out by going over is a relatively straightforward thing that you might have seen in either a Calculus 1 or a Calculus 2 or a Calculus 3 class. Most likely Calculus 2 and Calculus 3. I'd be very surprised if you didn't see this in a Calculus 3 course. So if you consider the sum from I equals 1 to n of all integers I, which is a sum of the form 1 plus 2 plus 3 all the way up to n minus 1 and n, this is equal to n times n plus 1 over 2. And this is a special formula because it's taking what's called an open form sum and finding a closed form expression for that sum in terms of the number of terms in the sum itself. And in general, especially if you've taken a Calculus 3 class, you will have seen that this is very, very difficult to do. It's not always possible to do, and the vast majority of sums, right, seeing what it is in terms of the number of terms in it, developing a closed form formula like we have on the right hand side is not easy. However, there are many sums for which we can do this, and if we have a formula like this, using induction is a very good way of proving the formula. This formula in particular has a very interesting history. There's like a legend that the mathematician Gauss, right, was a child, and he was in class one day, and his professor or his teacher at the time wanted to occupy students by having them add up large sets of numbers as busy work. So you tell Gauss and all the other students in the class to add up all numbers from 1 to 100 or from 1 to 1,000 to try to waste time and give them busy work. And within a second or two, maybe a minute or two, Gauss came back with the correct final answer, even for very large numbers. And his teacher checked, and he was very curious as to how he came up with this number, and it's this formula that he used to compute the correct value. So we'll see one basic method of proof without using induction first. And then we'll show how to do it using induction. So if we call S the sum of the first n integers, this is 1 plus 2 plus 3 all the way up to n. We know that addition in the integers the order doesn't matter, and so we have commutativity, for the order of addition, which means I can write this sum right here as n plus 2 plus 3 all the way, or no, plus 2 plus 3, n plus n minus 1 all the way down to plus 3 plus 2 plus 1. And Gauss noticed that if we add both of these sums together, we get 2 times s is equal to n plus 1. You have n plus 1, and you have n minus 1 plus 2, which is also n plus 1. You have n minus 2 plus 3, which is also n plus 1, and so on and so on and so forth, all the way down to 3 plus n minus 2, which is n plus 1, plus 2 plus n minus 1, which is n plus 1, plus n plus 1, and the sum simplifies to just n plus 1 plus n plus 1 plus n plus 1 n times. So they're adding n plus 1 plus n plus 1 plus n plus 1 n times, which means that 2 times s is equal to n multiplied by n plus 1, or s, this thing that we're looking for, is n times n plus 1 over 2. This concludes the proof. Now this doesn't, we didn't use induction at all in this proof, but the reason that I'm choosing this example is to show you that sometimes you can get a nice proof, a direct proof, just by using your definitions of addition in the integers or in the natural numbers. But the thing that we need to focus on here is that for many general sums, this is going to be much harder to do. So it's not going to be as direct as I've kind of gone through right here. In induction is the better way to go forward and prove statements of this form. So let's go through and try and prove this statement using induction. And the statement that we're going to be proving here is for p in the positive integers. Actually, I'll use k in the positive integers, so starting at 1. And it's going to be that p of k, or proposition, is the statement that the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. So we start by looking at the base case, p of 1 is going to be 1. On the left hand side, the sum is just 1, which is equal to 1 times 1 plus 1 over 2. This is 1 times 2 over 2, which is just 1, so it checks out. P of 2 is going to be 1 plus 2, which is 3, which should be equal to 2 times 2 plus 1 over 2. 2 divided by 2 is 1, and 2 plus 1 is 3. So this checks out. P of 3, sum is 1 plus 2 plus 3, which is 6. this should be equal to 3 times 3 plus 1 over 2. 3 plus 1 is 4, divided by 2 is 2, 2 times 3 is 6. So we've done 3 base cases. Each one of them has the statement has held for us. So now we have to make our inductive hypothesis, which is true as evidenced by the base case. This is that there exists integers, positive integers, such that P of k is true, and then lastly the inductive step is that we need to go through and show that for all k in the positive integers, P of k implies P of k plus 1. So to do this, we start by assuming P of k for some arbitrary integer k in Z plus. Which is to assume this right here, that the sum of integers from 1 to k is equal to k times k plus 1 over 2. And now the question becomes, how do we get from this assumption, we're assuming this is true, this is P of k, to what we're trying to show? Well, let's start with the left-hand side of what we're trying to show. We're going to show that the sum from I equals 1 to k plus 1 is equal to k plus 1 times k plus 2 over 2. So we'll start with the left-hand side of this. And what we can do is we can kind of rewrite this a little bit. We can say this is the same thing as the summation from I equals 1 to k of I plus k plus 1. If we consider this sum right here, and we sum all the way up to the kth term, and then add to it the k plus first term, which is just k plus 1 in this sum right here. And now we use the assumption P of k to rewrite this summation as k times k plus 1 over 2 and we can factor this, right? K over 2 plus 1 times k plus 1 and finally, if we bring this to common denominator, we have this is going to be k plus 2 times k plus 1 over 2, or k plus 1 times k plus 1 plus 1 over 2. And so we've shown that this summation is in fact equal to this formula in terms of k, which is exactly our predicate at P of k plus 1. And we can therefore conclude by induction, for all natural numbers n in the positive, for all n in the positive integers, P of n is true, which is the same thing as saying that the summation from I equals 1 to n of I is equal to n times n plus 1 over 2. And this ends our mathematical proof by induction. This is very, very clever. And it's important to really understand these examples because really every proof by induction using basic induction is structured in this way. So let's move on to another example, a similar example, just to kind of make sure that you really understand this process well. As I prove this statement P of n for n in the positive integers, that the summation from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. So we start with the base cases. And our proof by induction. In this case, P of 1, which is the statement that one squared, the summation from 1 to n of I squared when n is 1 is just 1 squared. This is equal to 1, which is the same thing as 1 times 1 plus 1 times 2 times 1 plus 1 over 6. And this is 2, this is 3, 2 times 3 is 6, 6 divided by 6 is 1, therefore this holds. P of 2 is the statement 1 squared plus 2 squared is 1 plus 4 is 5. This should be equal to 2 times 2 plus 1 times 2 times 2 plus 1 over 6. Which is a little bit more cumbersome to verify. However, it's not too bad. This is just 2 times 3 times 5 divided by 6. 2 times 3 is 6 divided by 6. This is equal to 5. So I'm just going to do these first two cases, right? Really, the base case, you only need to show the first case, but it sometimes kind of helps understanding a little bit more and really kind of clearly seeing what you're doing if you do the first couple cases. But so now that we have our base case done, we have to do the inductive hypothesis. Which is the statement that there exists a k in the positive integers such that P of k is true. And lastly, the inductive step So the idea here is that the inductive hypothesis, right, is evidenced by the base case. If you correctly show the base cases, the inductive hypothesis will be a valid hypothesis. This is why we kind of split this up into two parts. But now we have to do the inductive step, which is the step that we have to show that for all k in the positive integers, if p of k is true, then p of k plus 1 is true. So we start by assuming p of k, which is the statement that the summation from I equals 1 to k of I squared is equal to k times k plus 1 times 2k plus 1 over 6. And now we need to show p of k plus 1. So again, what I'm going to do is start on the left hand side of p of k plus 1, which is the summation of I squared from I from 1 to k plus 1. Just like before, this is the same thing as the sum from I equals 1 to k of I squared plus k plus 1 squared. And we know that by our assumption of p of k, this summation can be written as k times k plus 1 times 2k plus 1 over 6 plus this k plus 1 squared. And now you can see immediately this is going to be a little bit longer than before, but we can simplify this a lot. We can factor out k plus 1, and bring the 6 to common denominator to write this as, it'll be k times 2k plus 1 plus 6 times k plus 1 over 6 and if we rewrite this out a little bit more to kind of simplify, this is the same thing as k plus 1 times 2k squared plus 7k plus 6 divided by 6, which factors very, very nicely. This factors to k plus 1 times k plus 2 times 2k plus 3 over 6, and I only need a little bit more space here, so I'm going to make a little bit more space and try to finish this proof all on the same page. And this can be rewritten as k plus 1 times k plus 2, which is k plus 1 plus 1. And this is the same thing as 2 times k plus 1 plus 1. So we've shown that this summation is the same thing as this formula in terms of k plus 1, and therefore we've shown that p of k, if p of k is true, then p of k plus 1 must also be true. So therefore, by induction, we conclude that this statement has to hold for all integers n, for every positive integer n. So this is very, very neat, and I think clearly shows the idea behind mathematical induction. So the next example that I want to cover is a very, very, very important example in terms of counting finite sets. This is called the general inclusion-exclusion principle. Super important for counting, any number of elements in any number of finite sets of unions. Or suppose we have finite sets A1, A2, all the way up to AN. The proposition here that we're going to be using induction to prove is an extension of the inclusion-exclusion principle that we developed for 2 sets. And I wrote this down, what this is going to be for 3 sets and 4 sets as well, when I first introduced the inclusion-exclusion principle. But the idea here is that the cardinality of the union of n sets, n finite sets, is going to be exactly equal to the summation of the cardinalities of each individual set minus the summation over I and j, double summation, and we're only going to have when I is less than j because we don't want to double count any of these intersections. But it's a summation of the cardinality of the intersection of AI with AJ. But then we have to add back in the so-called third intersections, which is going to be the summation. It's actually a triple summation over I, j, and k of AI intersected with AJ intersected with AK, and we keep doing this alternating procedure. So we continue this alternating procedure all the way up to and including the final term here, which is actually going to be -1 to the n plus 1 times the cardinality of the intersection of all n sets. This is what's called the general inclusion-exclusion principle, and it actually holds for any number of finite sets. So let's go through and try and prove this using induction. Here we've used the union notation for the union of n sets and the intersection notation for the intersection of n sets. So we know that proof by induction is going to start with the base case. And our base case here is actually going to be for two sets, right? Where this statement P of n, we're starting at 2 sets, 3 sets, 4 sets, and so on and so forth. So the first statement here is P of 2, which is the statement that cardinality of A1 union A2 is equal to the cardinality of A1 plus the cardinality of A2 plus or minus the cardinality of A1 intersected with A2. And we proved this a couple lectures ago when we talked about basic counting and cardinality for sets. I didn't go through and prove proposition P of 3, and really we only need proposition 2 to do induction, but remember that the formula that I just described up here, and I also wrote this down in the previous lecture, this is going to mean that the cardinality of a union of 3 sets is going to be the sum of the cardinality of A1, the cardinality of A2, and the cardinality of A3, minus the cardinality of A1 and A2, of A1 and A3, and of A2 and A3. And then lastly we have to add back in the cardinality of the intersection of all 3 sets. So we didn't go through and prove this in the cardinality lecture, but I did write it down in motivation for this proof that we're going to be doing. You could write a similar proof to how we proved proposition 2 for this as well. It's going to be a little bit more complicated, but it's possible to go through and do almost directly the same way as how we proved proposition P of 2 here for 2 sets. So we're going to consider the base case done. And now we need to do the inductive hypothesis. Which is the assumption that there exists a K, in this case in the set 2, 3, 4, and so on and so forth, such that P of K, our base cases are covered by 2 and 3 here. And lastly, we have to start and prove the inductive step. Which is that for all K in the set 2, 3, 4, if P of K is true, then P of K plus 1 is true. So we start by assuming that P of K is true. is that this general formula holds for an arbitrary k in the set 2, 3, 4, so on and so forth. If this is true, then we need to show that p of k plus 1 holds. So just like before, what we're going to do is we're going to start with the union and look at what the union becomes. The union from I equals 1 to k of AI, or k plus 1 of AI is by distributivity the same thing as, or by associativity, not distributivity, is the same thing as the union of AI from 1 to k union set AK plus 1. Right, this is just saying that I can compute the union of the first k sets and then union to that the set AK plus 1. And this is just a standard example of distributivity. And because of this, we have that the cardinality of the union of all k plus 1 sets is going to be the same thing as the cardinality of this union of sets. But notice here that this is the union of two sets. And we've already proven our base case for two sets, which is that the cardinality of this union of two sets is going to be the same thing as the cardinality of this set plus the cardinality of this set minus the intersection of the two sets. Cardinality. And this is by the base case. You could say this, writing these two sets as this union is just by associativity. Of the union of sets. Right, I can order the unions in any way that I want. But what's neat here is the following. So we have two big things that we can do here. First, we can consider what the cardinality of this union is going to be of the first k sets. And by our inductive hypothesis, in our assumption at the very beginning of the inductive step that P of k, really just the assumption that P of k is true for some k in the integers, we have that sometimes called the inductive assumption. This summation right here is going to be the same thing as the cardinality of this union right here is going to be the same thing as the summation from L equals 1 to k of the cardinality of A L, set AL, minus the summation from 1 L less than M less than N of all of the first intersections of the sets plus, and so on and so forth. This alternation all the way up to -1 to the k minus 1 times the cardinality of the intersection 1 to k of all of the sets, the first k sets I should say. So this term right here goes to this first term right here by the inductive assumption. And then we also have to have the addition of the cardinality of ak plus 1, which is coming from right here. And we can also use distributivity here, the union of k sets intersecting with a third set, or a second set ak plus 1, as the intersection of a multiple union distributes, and this becomes the same thing as the union from I equals 1 to k of ai intersected with ak plus 1. So this simplification is due to distributivity. Of the union, or I should say of the intersection. So this is getting a little bit long here, however we can directly simplify this very, very, very nicely. We do this again by thinking about what this is saying. Well, we can kind of simplify this a little bit by saying that this is going to be, this sum plus this is going to be the same thing as the summation from L equals 1 to k plus 1 of the size of AL. So this can be absorbed into this summation notation rather easily. And we're still left with all of these terms However, this is the union of k sets, k specific sets, which means that again here we can use our inductive hypothesis, which is that the cardinality of the union of k sets is going to be the same thing as the summation from L equals 1 to K of the size of AL intersected with K plus 1, AK plus 1. This will be minus the summation from 1 less than L less than M less than N less than K of third intersections, or I should say of second intersections, but you have AK plus 1 tacked on here, so it'll be AL intersected with AM intersected with AK plus 1, and so on and so forth. We continue this process all the way up to the final term, which is negative 1 to K minus 1 times the size of the intersection from L equals 1 to K of AI, right, AL intersected with AK plus 1. So just the intersection of all of these sets right here. So and just want to point out again that this is again by another use of the inductive assumption. On this union right here, the union from I equals 1 to K of AI intersected with AK plus 1. Because this is just, again, the union of K sets, so we can use the inductive assumption. But what you're going to note here is that I can actually combine term by term everything in each one of these sums. So, for instance, this sum right here is all of the first intersections of the set K plus 1 in all of the other sets. Well, and this index right here should be K, because K is our maximum index from before. But so the idea is that this sum of all of these sets to all of these sets is now just including all of the first intersections with K plus 1. And this same idea happens for the third intersections and the fourth intersections and so on and so forth, all the way, by the way, up to and including, right, this final term right here. And so grouping these things together, we have that this is equal to the summation from L equals 1 to K plus 1 of cardinality of AL minus the summation from 1 to K plus 1 of all of the size of the first intersections plus the summation up to K plus 1 of all of the third intersections and so on and so forth, all the way up to this final term which is going to be negative times negative 1 to the k minus 1, which is negative 1 to the k, or k plus 1 minus 1, times the intersection from L equals 1 to k plus 1 of all of the sets from 1 to k plus 1, because k plus 1 is included in each one of these intersections, so this is really just the intersection of all k plus 1 sets. And what's amazing here is that this we've shown then is equal to this, and essentially now what we've shown then is that if p of k is true, then p of k plus 1 is also true, because this equality is the statement p of k plus 1, and we've used only the statement p of k to prove this. So we can then conclude the general inclusion-exclusion principle. So the last thing that I wanted to talk about and just kind of explain was the concept of strong induction, which is sometimes seen as a better way of using induction, and or a different way of doing an inductive proof. And I'll explain this as follows. So the idea behind strong induction is that we actually go through and we say we're still trying to prove that the statement p of n is true for all positive integers or all natural numbers, where p of n is a propositional function or predicate. But the idea here is that we still do a base case, where we have to verify that the proposition p of 0 and possibly p of 1, p of 2 is true. But then the inductive step here is a little bit different. The inductive step is to show that if P1 and P2 and P3 and all the way up to PK is true. So if all of these statements are true up to K, then P of K plus 1 is true. And this is important because this means that sometimes in order to prove something using the inductive step, we can't just take if P of K is true. We need multiple previous examples or previous instances where the statement is true. And we kind of saw something like this in this proof right here, the proof of the inclusion-exclusion principle, because you note that part of the proof here is using, in this step, the base case in our, or P of 0 in our assumption. So a strong induction proof uses and proves the implication if P1 and P2 and P3 are all the way up to I'll start at P0 here. You can start it anywhere that you want in an induction proof, but because I'm starting at P0 up here with the base case, I should start it down in this notation as well. And so the inductive step is to show that if P0 and P1 and all the way up to PK is true, then PK plus 1 is true. So we can get to prove this conditional statement. So it's sometimes called the second principle of mathematical induction or complete induction. But the idea here is that this complete induction is not a very good choice because it's not like the other form of induction is incomplete. But the idea is that you can actually show that mathematical induction that we presented earlier and strong induction are actually equivalent, which means we can show that each can be shown to be a valid proof technique, assuming that the other is valid. But the idea here is that it's good to go through and sometimes use strong induction. Sometimes for certain proofs you have to use strong induction rather than regular induction in order to show the inductive step. And so much so that many mathematicians will sometimes only use strong induction here. But this will conclude today's lecture. Thank you very much for tuning in. I hope you have a fantastic day and that you learned something.